Our speaker today, Professor from Renesse from French University, and I'm afraid that it is a great opportunity for us interesting that now we have a seminar with the speaker and participants in the room, not only via the internet. So we are happy with this subject, and Max are going to speak about volume motion of the space and Dean-Kawasaki models. So please.
Thank you, Andrei Anatolyevich. It's a great pleasure to be here. I had the opportunity to talk to several members of your group and to the head of the group yourself. I can say that I'm really impressed by the scientific work that you do. It's a great pleasure to be at this wonderful place. Thank you. It's an honor. Am I audible in the internet? Can you hear me well enough? Okay. Thank you. Okay, so I will give a talk which is designed to be a survey talk on work that I did over many years. It will be probably boring from a honest, true Russian mathematical style of point of view, because I will not give many details in what I will talk. I will try to give a survey of different results which all belong to some sort of a program on which I have been working since for years. And I hope that I can make some advertisement for the program, because it will show that we have a lot of common interest in what I'm interested in and what you are interested in this group. And one of the most important names that will appear on almost every slide in this talk is the name of Vitaly Konorovsky, who is here with us today, and who has been working with me over several years now on this project, and I had the pleasure to be his collaborator. And there are other names who did some work with me on this. One is Sebastian Andres, who used to be a PhD student. Tobias Lehmann is another PhD student who finished. And then there is my former PhD advisor, Karl Theodor Sturm, who also played a role in the development of these things. Okay, so thank you again for the invitation. I start, I have approximately 1 hour time, or let's say less, for the talk, and here's the outline of my talk. I will spend a lot of time with the motivation part of my talk. I will introduce the problem that I want to consider in full detail. Then I will introduce to you what is called the Dean-Kawasaki equation, which is a stochastic partial differential equation, which is in a way the dream equation that we would like to solve. And then I will tell you that this dream equation that we would like to solve cannot be solved, or cannot be solved to give interesting results. This is a result that we achieved together with Vitaly in 2019, which is a negative result in a way, or a rigidity result for this stochastic partial differential equation. And then I will tell you some alternative versions of solutions to this kind of equation if we modify the equation a little bit, so to say. And we will discuss 3 different models which give solutions to this equation if we allow certain modifications. And these 3 different types of models are related, of course, but they are different in certain details, and they were developed in different times and in different years. And I would like to give you some overview of these different models, and I would like to make some advertisement invitation to probably also do some research on this or on related questions. So that's the plan of the talk. And as you can see, Vitaly's name is showing up almost everywhere because he was an important cooperation partner in these different developments. Okay, we start with motivation. So the framework that I shall work with is this optimal transportation theory, which was fashionable over the last 10 years or 15 years even, or even 20 years if you like. This is a special geometry or a certain geometric perspective on the space of probability measures. It comes with the name of Monch-Kantorowicz-Wasserstein distance. And people in analysis, so this optimal transitation problem is a classical problem in optimization, also in probability theory. But people in the theory of analysis of evolution equations became very interested in this Wasserstein distance by, for instance, the work of Felix Otto, who in 2001 gave an interpretation of this space of probability measures equipped with the Wasserstein distance as an infinite dimensional Riemannian structure. So this slide here assumes that you are familiar with the concept of a Wasserstein distance. So probably I shall invest one slide on this. 1 second, please. Now I need to be careful with my program that I don't do anything stupid here. Yes. Okay. So here is an empty slide. So let's just recall to everyone what the Wasserstein distance is in definition. So you give yourself two probability measures. Let's call them pi, or let's call them mu and sigma, which are both probability measures on the d-dimensional Euclidean space. And then the quadratic Wasserstein distance for these measures is defined to be the infimum of the distance squared, x and y, which you integrate over all coupling measures p in the set gamma defined by the set mu and mu, right? And this is now an integral over the Euclidean space squared. So this is a mutual distance. And this set gamma mu nu, we say a measure pi is in the set gamma mu nu if and only if, well, pi is a probability measure on the product space. And it needs to satisfy that the first marginal, so if I write it probably like this, marginal times the projection to the first coordinate, if that is mu, and the second marginal of this probability measure is nu. So in this case, we call pi a coupling measure. So the probabilistic interpretation is clear. We have a certain random variable whose distribution is mu. You have another random variable whose distribution is nu. And in some sense, you have an optimal joint random variable in two variables in double coordinates, which has the right marginals, but that produces some coupling between the two. And you want to have an optimal coupling in such a way that the distance between the two realizations of the random variable is minimized in expectation. This is the quadratic Wasserstein distance. And here in this infimum, I have to write in power 1/2 for homography. So, okay, so it's an important and natural notion that probability Okay. Okay, we are back and connected. I hope that are with us. If not, oh yeah, we have some people. And now I need to share my screen. Okay, so recall that a Riemannian manifold, so it's just a topological space with a chart, and then you have points and you have tangent spaces, and you need to, if for identifying a distance between 2 points, in some sense, you need to find the minimal energy curves. So you need this concept of tangent space. So that's the classical picture of Riemannian manifolds. And what Felix Otto suggested is to view this, okay, and this gives notion, so this Riemannian distance gives notion of a distance between 2 points. So this minimizing the energy between two points in the manifold P and Q, you minimize over all possible, say, curves, and if you have a notion of energy of such a curve, then this energy concept of this Riemannian tensor on each tangent space then produces a distance on an intrinsic notion of distance on this manifold. And what Felix Otto suggested was some sort of an infinite dimensional Riemannian tensor calculus on this space of probability measures. This was this insight. This space of probability measures equipped with this Wasserstein distance can be understood as an infinite dimensional Riemannian manifold, where if you sit in one curve, if you sit in one manifold, so for that purpose, at each point of your manifold, you have to specify what is the tangent space. Okay, the tangent space of a measure is the space basically of all redistribution. So it's a space of all velocity fields. Honestly, I honestly.
It is Andrea. Just Andrea.
Reconnect just now.
€1,000 or so. Wait a second, I need to reconnect. I guess I need to re-share my screen. So I apologize for the difficulties here. I think my computer has a very bad virus, and it destroys everything that is in the neighborhood of this computer. Okay, so probably I spent a few seconds on this slide because this is in a way the most important slide of my talk. I really love this, what I present to you at this moment. It's not obviously it's not my invention, but I can tell you that many people fell in love with this interpretation of optimal transmutation. This paper by Felix Otto had a huge impact on the mathematical literature. And so let me say it again. So if I want to specify a Riemannian structure on a certain collection of points, a Riemannian structure, I need to say what it means to move a point infinitesimally, and I need to say what it actually costs to move this point infinitesimally. Okay, so now a point is a probability measure. This is a state of my system. So if you like, let me be really slow. I know I'm talking to a very, very exquisite audience, but nevertheless, let me be really slow. So mu is a point in my manifold now. Here, a point means I have a certain state of the system, which is a mass distribution. And the most natural thing to infinitesimally change a mass distribution is to propagate my mass distribution by a gradient vector field in some direction. So I have some gradient vector field, I can solve the flow equation, and I can propagate, I can just move the mass around. And then the continuity equation, or the local conservation of mass, tells me that the infinitesimal perturbation, if I do a d by dt, the infinitesimal perturbation, which is mu dot, is then given by this expression. It's minus divergence of mu grad. It's just a continuity equation or local conservation of mass. This is just a standard thing in continuum mechanics. Okay, so this is how this mu dot is one possible admissible infinitesimal variation of my probability measure. And now I have to specify how much it costs. And Felix Otto suggested to say, okay, the cost, the infinitesimal cost that comes with such a perturbation is defined to be the kinetic energy. Recall that I propagate my I propagate my mass with a gradient vector field. So that means that every particle at this moment of time moves according to gradient f at that moment. And then you can ask me, what's the natural notion of energy for this motion? Well, it's just velocity squared times mass, which is kinetic energy. This is just kinetic energy. Okay, fine. So that's the concept. So I can write this in a slightly more elegant form because I need to invert, if you like, this weighted Laplace operator, but it doesn't really matter. But anyway, this comes with a yes. Yes. No, here it's not yet integration. I mean, please ask the question in a little moment again. So this interpretation here is completely formal. There's no hardcore mathematics, but this interpretation just gives you ways to interpret things, and later you have to prove things by hard arguments. But this is just picture. But it's a very nice picture that many people love. Now comes the point. So now we are doing this game here. But recall that our manifold now is this infinite dimensional manifold. So this is a certain mass mu. And this is a certain mass nu, right? So we are having this infinite dimensional picture now. And now I can do all kinds of vector fields which drive my mass distribution from one mass distribution to another. And I can do this minimal energy game. I can find geodesics in this picture, which means that I have one.
Okay.
But now
Yeah, sorry, we have another connection problems here.
I'm sorry?
I just also
Yes.
that.
Okay, I have another idea. I do it directly with this. I connect directly with this guy, but people will not see me. They will just hear me.
And you can put that number.
Yes. Let me just recommit. That's probably the best way to do it. What's we are both? That's I need to have the right link for the Okay, let me try to connect directly with this guy.
Yes,
I need to. Okay, sorry for this difficulty. So I continue my talk. Am I audible to the people online, or can people online hear me? I mean, if they ever want to hear me.
Yes, yes.
But can people online hear me or not?
Yes, we can.
Okay. I apologize for this complication. Okay, so we have a notion of admissible infinitesimal variations, and we have a notion of what it means to have the energy of this. And then we can play this game that we have two mass distributions, and we want to find in optimal fashion a connection. So in some words, you can, in some other words, you can also think of this. Let me introduce another slide. So in a way, it says this. So you could think of a starting distribution. This is, if you like, this is RD. I write this or R2. And think for a moment that our initial distribution is just the uniform measure on this omega. And our target distribution, this is a target distribution. Or let's even do something bad. Let's suppose we want to have a target distribution which consists of two blobs. We have two sets, and this uniform distribution on these two sets is our target distribution, so jointly. Suppose the two sets have the same volume, and suppose that this two is, so in a way, this is two different configurations of a swimming pool where you have a blue substance or a red substance in the swimming pool. So all this is, if you like, embedded in some water. You have a red piece of paint in the water. And now the question is, how can you turn on some turbine or some floating mechanism, some vector field, such that as the effect of this floating procedure, this initial blob is moved into the two other blobs. And of course, at each moment of time, you pay a certain amount of kinetic energy. So that there are various ways to transport by some turbine this guy into these two blobs. But there may be more efficient and less efficient methods. And the question is now, what is the most efficient method in terms of kinetic energy? This is exactly this minimization procedure, which is here, but now in an infinite dimensional context. You're trying to find curves which connect one mass distribution to another. And you want to do that in an optimal fashion. And if you compute the minimal kinetic energy that it takes to do that, you recover the quadratic Wasserstein. So from that point of view, the space of probability measures equipped with this quadratic Wasserstein distance is an infinite dimensional Riemann manifold. And now we can also consider, now we can do analysis of this Riemann manifold. For instance, we can study dynamical systems which make use of this geometric structure. So for instance, we can study gradient flows. Like we have a certain function and we want to minimize it, and we go in steepest descent dynamics, but using steepest descent according to this geometry. And if we take, for instance, the steepest descent dynamics, which comes from the entropy, So if you give yourself a measure mu, you can compute the entropy with respect to a uniform measure. That's a function on this infinite dimensional manifold, and you can consider the gradient of this functional, and you can do a gradient descent dynamics. Mu dot equals minus gradient. And if you write down what this actually means for this particular geometry, you recover heat equation. So heat equation, from this point of view, is heat equation because a system wants to minimize its entropy as quickly as possible, but each point of each time step, the cost to pay for minimizing the entropy is kinetic energy. And so this is a dynamic equilibrium, so to say, between entropy and kinetic energy. And this is, of course, a very, very nice interpretation of heat equation as a natural physical system. So everybody who saw this, I mean, for the first time was very, I mean, that I know, was totally happy because this gives, if you like, a physical geometrical reason why heat equation is there. The system wants to minimize entropy and it performs heat flow because it has to pay kinetic energy, and this geometric context gives exactly the right picture. Now, around the same time, or effectively something before, the French mathematician Jan Brenier realized that the geodesic equation, so if you just have geodesics in this geometry, basically means that this is compressible Euler equation. This is a first order equation here, first order dynamical ODE, and the geodesic equation would basically correspond to the equation mu dot equals 0. This would be a second order ODE, right? So in this geodesic equation, so in the Riemannian, in Euclidean space, the geodesic equation reads like this, right? So this is the motion of, this is the ODE for straight lines. This is the geodesic equation in RD for a dynamical system. And if you are on a Riemannian manifold, you would need to write, this is the right way to write the geodesic equation on a Riemannian manifold when you say the acceleration of a curve is 0. And you can write this geodesic equation also here in this infinite dimensional context, and this would read basically like this. And then if you write down what it actually means, it says that the system, this corresponding measure value process, which is described by this very short notation, is a compressible Euler equation. So a very natural, the compressible Euler equation is basically the starting point for a Navier-Stokes equation. Now, I did also some computation in this business because I like this so much, but I was not alone with this inclination. You can also write slightly more complicated equation. This, namely, not only the geodesic equation. You can not only write the geodesic equation, but you can also write Newton's law. So recall Newton's equation. It says acceleration x dot dot equals force, and in most interesting cases, force is a conservative force, is a gradient of some energy. So this equation here is Newton's equation on a manifold. So you have a particle which is being accelerated by a force, by the gradient field the force is the gradient of an energy. That would be a Riemannian Newton's law, classical law of motion. And now if you make a particular choice of these function f, which associates an energy to a probability measure, then you make the choice of the Fisher information, which is a quantity from statistics. Here you can write it as the norm, gradient norm of the entropy, and you additionally take the mean value of the measure against a certain potential function mu. Then you find that these solutions, this dynamical system gives rise to solutions to the Schrödinger equation of quantum mechanics. And how is that done? Well, this is a dynamical system of second order. So you have a vector field effectively at each moment of time. So this is a dynamical state of the system. It comes with a certain state at every moment of time, and it comes with a certain gradient velocity field. You use these two data of the state of the system, and you construct with these two data, you construct this complex valued function. This is an arbitrary complex valued function, so to say. But if you write down the PDE that this complex valued function is solving, you find that this is a complex valued function which solves the classical Schrödinger equation from quantum mechanics. And what you also find is that this is a symplectic isomorphism, so to say. So in dynamical systems or in physics, you learn that two dynamical systems, two Hamiltonian dynamical systems are the same if there is a morphism between those state spaces, which is a symplectic isomorphism. And you can do these infinite dimensional calculations. It's all formal, but you can see that this transformation, which maps this dynamical state of probability measures into a wave function, that this is actually a natural symplectic isomorphism, and it converts these solutions of a classical Newton's law, but in infinite dimensions. It converts these classical trajectories into solutions of the Schrödinger equation. And I would like to highlight that the choice of the appearance of the complex time here, so to say, is a result of this coordinate choice. So from this, you could say, okay, since it's a symplectic morphism, the Schrödinger equation and Newton's law and this probability measure is just the same. So, and whenever you come to teach quantum mechanics the next time, and you don't like to explain wave equation or wave functions, you can also just explain optimal transportation and say that this is a natural dynamical system on probability measures, and no one will have any trouble with complex time and wave equations. Okay, so we have now made a couple of steps. We have introduced this infinite dimensional Renesse calculus. We have identified the optimal transportation distance. We have studied first order ODEs, which give rise to heat equation, which is a fundamental equation. We have second order geodesics, which is compressible Euler. We have Newton's law, which is the Schrödinger equation of quantum mechanics. And of course, the next question that you would have if you have a probabilistic background is, okay, once we can do all these fantastic dynamical systems on this space, what's Brownian motion on this space? This is the logical next question. If we can do all these nice dynamical. Okay, and this is a slide that I have already shown in my last appearance here in this seminar. It's a slide which I always show. It's about Brownian motion on manifolds. So I want to do this. I want to construct now a Brownian motion on this Wasserstein space, right? That's my dream project since many years. But for that, you should probably recall what a Brownian motion on a manifold is. But you cannot see this slide. Oh no, I'm disconnected again. But this thing has not a bug.
This is bad internet connection.
This is now, I'm sorry. I'm sorry. Oh, I apologize. Is this the fault of my tablet? Is this the fault of
the internet?
How do you share? I mean, do you have on your laptop some special program which allows you to share your screen or what you write to directly to the laptop?
I can. This cable here has no meaning anymore. I can just disconnect that entirely. I think because I'm connected through Zoom with this. And now.
Are you connected through Wi-Fi or?
I'm connected here through Wi-Fi with your network now. I'm just connected with my tablet to the Wi-Fi of the institute.
Wi-Fi is very good here.
Okay.
I will tell you. I thought that we have it is a button. Once again, because
Yeah, 1 second, please. It's what is it again?
Android.
It's not shown. It's not shown.
Just move somewhere or just Android. EBCC 6474.
Yes, okay. Okay, I hope you understood what I was trying to say. So they're a nice dynamical system on this infinite dimensional manifold. And so the question is, can we construct a Brownian motion on this infinite dimensional manifold? To recall what a Brownian motion on a manifold or a metric space is, basically it is constructed by central limit theory of geodesic random walks, right? So if you have a metric space and you can jump uniformly in these spheres, then you can do basically a hydrodynamic scaling. If the space is good, you can do that, and you obtain a stochastic process with continuous trajectories, which is a candidate for Brownian motion. And what you will see also is that the Brownian motion exhibits the Riemannian distance through this short time asymptotics, which is called the Vassal formula. So that's Brownian motion on a standard smooth manifold. And let me emphasize again, every process on a smooth manifold can be called Brownian motion as a necessary condition only if it satisfies this asymptotic formula, because it says that the heat kernel, so to say, has exactly the right exponent in the time. And now the question is, can we do a similar thing on this infinite dimensional space? And if you think about this is not the only way that you can construct a Brownian motion on a Riemannian manifold. You can also use stochastic differential equations on charts. And if you do stochastic differential equations in this case here, you would probably see a stochastic partial differential equation, because we are doing stochastic differential equations in infinite dimensions now. And the stochastic partial differential equation, which more or less naturally comes out of these considerations, is this stochastic partial differential equation. So I'm saying, if I don't do, let me say again what I just said before, one way to define a stochastic Brownian motion on Riemannian manifolds is to do this geodesic central limit theorem. Another way is to use stochastic differential equations and then use charts and map it back. And I'm saying here that if you wanted to do a stochastic differential equation construction of such a Brownian motion, in our particular case, you would probably derive a formal stochastic partial differential equation, which is of this type. So it has a drift part, which is just the heat equation part. That's your drift part in this stochastic differential equation. And then you have a white noise part. But of course, since this is a Riemannian situation, you would not expect a white noise which is independent of the state, because you're in a Riemannian manifold. You would expect a non-trivial sigma, so to say. If that's x, this is of course b of x dt. So that's the drift part, like a vector field. And then you would expect this as a non-trivial transformation of the noise at each moment of time. And this sigma tensor, which is a matrix, in this case it is an operator which transforms the noise. And the operator here is divergence of grad of mu dwt. That's just a natural, so to say, stochastic partial differential equation. If you look at this, if you want to construct this process. Now, if you look at this equation, and if you come from measure valued processes, then you know that this equation, except for the divergence. If you write an equation like this, d mu is beta Laplace mu dt plus square root of mu dwt. This is now a quiz game for everybody in the audience. Does anyone know this stochastic partial differential equation? Bingo. The blue stochastic PDE is exactly this Dawson-Watanabe or super Brownian motion stochastic partial differential equation. One should say that here in the Dawson-Watanabe or super Brownian motion, this is scalar white noise. Here we use vector valued white noise, and here we use and we have this divergence on top of it. But if anyone is happy with this as PDE, then you should have no fundamental problems with looking at the green as PDE, because it's pretty similar in its appearance, except for the divergence. And this is a formal representation. I mean, in Dawson-Watanabe super processes, the measures are not continuous. They in higher dimensions they are even singular, right? So, but people still write this square root of mu, and they understand what they have a clear understanding what it actually means, even if they are really bad measures where you cannot take the square root. And we do a similar thing. Okay, so this equation appeared in my notes very, very early when I started doing this. And many years later, a friend of mine told me that this equation has a name in physics. It's called the Dean-Kawasaki equation. And it is appearing in many places in the literature. It is something like a field theoretic description of a noisy particle system, so to say. Or stochastic field theory, so to say. So people really study this equation to derive properties of materials. And Vitaly helped me to actually say something substantial about this equation, which is the first rigorous result of my talk. And you might have seen this talk already by Vitaly previously. So first of all, so this no-go result, this is now the first rigorous result that I shall present, is about the question of existence of solutions to such equations with the divergence. I would probably in this audience, I can make also this remark. Sorry. If you look at this, I'm sorry, I should have written on a second layer. Let me just erase all this. Yes. If we look at this noise term here, I can write this noise term in a different fashion. I write this as a divergence of what? Of mu times 1 over square root of mu times dwt, if you like. I have done nothing, obviously. I have just multiplied by square root of mu and divided by square root of mu. But if I call this guy psi for a moment, psi t, if you like, what I see is that this is, again, my favorite continuity equation. So, and I forget about the Laplacian. So what I'm having is d mu t equals something, which is a deterministic evolution, plus a continuity equation. So again, I'm pushing around the measure mu, but with a random vector field. But the random vector field is so scaled in such a fashion that the fluctuations, so this is, if you like, the characteristics of this noise field depend on the actual state of the system. This is, so again, this is a continuity equation. As if you were translating the measure mu in the direction of a random vector field psi, but here the random vector field psi is scaled in its fluctuations in an inverse proportional way to mass density. That's very important. Okay, now comes the no-go results. Okay, let's first define what is a solution to this stochastic partial differential equation. I'm saying a measure value process is a solution to this Dean-Kawasaki equation if and only if mu is a continuous process assuming values in the space of probability measures, and it solves a certain martingale problem. Namely, if I take a smooth compactly supported test function and I test against a test function, the process, and if I subtract the drift part, the part of bounded variation, where I do one integration by parts in order to map the Laplacian onto the test function, I want that this is a martingale, which is just a standard thing for the martingale problem. And I want that the corresponding quadratic variation process of this martingale has this density, has this form. This is the standard formulation of Dawson-Watanabe super Brownian motion. For those who know it, if you don't put the gradient here, and just have an f squared, this is exactly the concept of a weak solution to the Dawson-Watanabe super Brownian motion, PDE. But here comes the gradient square. So therefore, this notion of a solution is very straightforward. And now comes the result that we obtained with Tobias Lehmann and Vitaly from several years ago, but not too long ago, is that we can solve this equation if and only if beta is an even number. And in this case, the solution is given simply as the empirical process for n independent Brownian motions. So, okay, you can say we have a Wasserstein diffusion because, okay, I will say that in a second, but this one will not be really an infinite dimensional process and only for very, very special scaling regimes. Okay, so these are the two, this is a rigorous result, obviously. or not obviously, but it is a rigorous result, and it contains two different ingredients, and if you put them together, you will easily be able to produce the result yourself. These are only the two pieces of proof that I give in my talk. First of all, you write down what the log-Laplace duality for this process. By the very specific algebraic structure, you have a nice Ito formula in case when you assume you have a process. You can write down this exponential, there's an exponential Laplace duality here. People know in Dawson-Watanabe process theory that there is this log-Laplace duality, and we have a similar log-Laplace duality. But in our case, the log-Laplace duality has a very explicit structure, so we can compute the nonlinear semigroup, which governs the log-Laplace duality in this case explicitly, and it is basically given by Hamilton-Jacobi-Bellman equation. So for that purpose, we have explicit duality, which in particular says that we have uniqueness in log for this process, if there is one. And the second lemma is about the generating function of a non-negative random variable. So if you have a non-negative random variable and you write down this probability generating function, and if it is so that this is a smooth function near the origin, then the corresponding random variable must be integer valued almost surely. So this is a characterization of integer valued random variables in terms of the probability generating functions. And if you apply this lemma to the explicit knowledge you have about basically these probability generating functions, you can easily conclude that these guys here must be integer valued quantities. And that allows you easily to conclude that the beta parameter must be an integer. So that's a simple proof. And it's we are very proud, I have to say. I mean, we are really very proud of this result for two reasons. First of all, it is an equation which was studied in physics since long, and people in physics wrote it down and always wrote it's a very difficult equation. We actually do not know what it actually means because of the square root and diversion and stuff. And so it's the first mathematical rigorous treatment of this equation, which comes with a probably disappointing result. Okay, but we address a really real honest question in physics. And the second thing which is very nice about this thing is just two lemmas which we put together. So nowadays we have this very high-tech theory about regularity structures in SPDE and all this. And this is a very bad SPDE, and people try to attack it with this. But this here is just nothing in terms of mathematical technology.
So it seems that if you have such a kind of equation due to this divergence,
Yes.
You just keep the structure of Brownian motions.
Exactly.
So if you suppose that we have just one point concentrated Brownian motion,
Yes.
then you have
exactly the structure. Exactly.
And due to this divergent term, you can just like balance it.
Yes.
We face the same effect when we consider when we try to consider SPD with noise, and we understand that this guy in the drift.
Yes. Exactly. It's exactly. So the typical SPDE theory, deals with situations when this guy is still dominating somehow the noise with his semigroup or D'Aprato subject. It's all about domination, that this guy is stronger, still stronger than this guy here. And here we are exactly in the regime when they're exactly on the same level. But okay. And now comes something that I can really say in this audience. The problem about when you read the papers from physics literature about the Dean-Kawasaki equation, people say that this equation somehow describes particle systems in the regime between law of large numbers and hybrid and fluctuations. It's somewhere in between. For us, this is a difficult statement. Because we as probabilists, we don't think there is something in between, not so much, at least. At least you are in very crazy situations. So how can it be that some system is at the same time law of large number and fluctuations? It's a different idea.
Maybe they mean this Martin Vassal stuff from one side.
Yes.
And from other side, they mean in dynamics that you have no.
Yes, exactly. But this, in a way, clarifies, in some sense, clarifies the discussion. And now I come back to something that I did long time ago, and that, so the question is there some system which actually really lives between law of large numbers and central limit theorem? And here comes something that does the job, and this is something that we did a long time ago. So here I'm considering a model. So I'm saying I'm going to the next step in my talk. I'm going to present as time permits. I will probably make some choice. So probably I will have 5 or 10 minutes extra time, but then I will stop. Yeah. But I hope I can finish in 10 minutes from now or something. So I would like to introduce 2 models. One is something that I did without Vitali, and the other one is something that I did with Vitali. So here's something that I did without Vitali. That is, of course, a long time ago. So this is a system of particles. So the rest of the talk will be in 1 dimension. So basically, let me just try a picture. So now I'm like this. I have a mass distribution, and I want to construct a random process of mass distributions. So this guy is now some random probability measure which moves. The next moment it's this or whatever, right? So, and my mass distribution, this is, in this audience, you will all have no problem if I imagine this mass distribution as a collection of probably interacting particles, which sit at some concentration on the real line, so they move. And here I'm having, so let's rotate the picture. And let me focus on a particle system whose simulation you see here, for instance. So 3 different simulations of the same particle system. There is a parameter beta, and you can think of beta being a small, very small parameter. And so here, what we have here is and here's a particle system of 1, 2, 3, 4 particles. And the particles, if you like, they start at some initial condition, but then they have attraction to one another. They have electrostatic attraction. So each of these particles has a left particle and a right particle, and they see each other. Or each particle sees its neighbor to the left and to the right, and he has an electrostatic attraction to that neighbor. And on top of this, he is driven by a Brownian motion, and then I have some local times which, okay, depending on the precise regime, which prevent that the particles overtake each other. So that by this, I just want to enforce that the particles don't overtake each other, so they keep the order. And then I have this minus guy in front basically makes sure that the particles want to go to the next neighbor. And then I have a little bit of a compensation. So n is the number of particles. Here in this case, it would be 4. N is the particle number. So there is a compensation which counteracts this attraction by a scaling factor which depends on the number of particles. So this is what a physicist would probably call an anharmonic chain model. It's anharmonic because it's not a quadratic interaction. And it's electrostatic. It has this electrostatic rule, and the strength of the electrostatic interaction is a little bit scale. And now we can pass to the corresponding empirical process for this particle system. We can pass to the corresponding empirical process of this particle system. And then, in long time ago, we showed with Sebastian Andres that you can pass to a limit, to a high density limit for this particle system. This corresponds, of course, to a measure valued Markov process. And this measure valued Markov process solves in an appropriate interpretation this Dean-Kawasaki equation.
But I see additional terms.
But with an additional term, which is some sort of a renormalization term or something like this.
Maybe it helps.
Yes, this is an important term. But the curious thing is that we have no, I mean, it's a strange term. We cannot really, up to this point, this is a very strange distribution. It's a very non-linear distribution. Yes, no, yes, I'm not sure. To be honest, I'm not sure where it comes from. It comes actually from singular interaction of the particles when they meet each other. And okay. And we have an invariant measure for this particle system, which can be described in terms of the Poisson-Dirichlet process. And what we can also find is that this process, okay, we should also say that this process assumes, so the typical measure that you see under this dynamics will be a Cantor type measure. So it will be not, it will not have atoms, but it will not be absolutely continuous. So it's not a finite particle system or whatever. It's not the Dean-Kawasaki situation. It's really a diffuse thing. And this thing here, beta is a free parameter. You can do it for any positive beta. Remember that in the Dean-Kawasaki situation, we had a fixed beta. So in some sense, this guy and this guy, they live on the same scale. These guys compensate one another in a way. Here now in this system.
You said that you cannot have absolute continuous measure.
Yes. Yes.
Cantor dust.
Yes, right. It's a Cantor dust type. Yes. Okay. But nevertheless, the beta, yes, the beta helps you. Without the beta, okay, so this would be the transition to the next.
Let me ask you the question. Can you just show us the gain equation? Yes, no, this one. Your equation. I see. So you said that it doesn't depend on beta at all.
Well, you can know it depends. The limit process depends on beta, but I can do the procedure for any beta.
Normalization only
In front of you.
Near
Yes.
term,
Yes.
but not with local types.
Yes. Yes.
The nature question is why the sum of local types doesn't work. Interesting.
We did not ask the question whether local times grow, but I mean that the process basically piles up local time a lot. So yes, to some extent you could say that the local time is a dominating feature. Yes.
I mean, the problem is how you choose balance of these two drifts related to local time and related to TT.
Well, to be honest, so we didn't. I cannot tell you why it is so, but I can just tell you that we were lucky to find. We did the following things for the proof, if you like. So first of all, this sequence of measures, this sequence of processes has a very clear sequence of invariant measures. On a simplex, more or less, on a more bigger simplex. And we have explicit knowledge about the invariant distribution. So there's some Dirichlet form behind. And we can just verify by Dirichlet form methods that the corresponding sequence of empirical processes is tight. And we identify on the level of Dirichlet forms the limit, we do a limit on the operator level. So it's not really stochastic analysis that we do. We just identify the analytic the analytic objects that govern it, and then
Don't claim, but we claim with convergence. So
yes. So the tightness is not a big deal. I mean, the tightness is not a big deal.
because of the ordering.
Yes. And so this is our process, which has these Cantor dust type measures, and we can show again by Dirichlet form methodology that the short-term asymptotic of this process is given by this Wasserstein distance.
What about estimation? Because usually when we try to have estimation for the density of the candidate with Brownian motion.
Yes.
Like initial mesh are and so many people did, then we need structure of curvature on a given manifold. So did you try to find some estimation?
No, I think the curvature here is really, in a way, the curvature here is rather a negative minus infinity curvature situation. But again, I cannot. Here again, we were lazy and lucky at the same time. This is Dirichlet form. We are using again Dirichlet form technology, and the Dirichlet form basically has this the energy part in the Dirichlet form. Well, let me say it for short. There is the notion of an intrinsic distance with this reversible process. And then there is an abstract meta theorem, Dirichlet form theory, that if you know the intrinsic distance, then the heat kernel in its weakest interpretation will satisfy this Gaussian estimate on short terms with respect to that intrinsic distance. And so the work is, again, an analytic work to analyze the intrinsic distance that comes with this Dirichlet form. And this is what we do here. And then we just use this meta theorem. So we were lazy and lucky at the same time. Using a big theorem from Dirichlet theory, we just need to identify the structure of the form. Yes. Yes, sure. The next model, and I will do that shortly. The next model is what we call the modified Arasia flow. This is how Vitali really came into the theory. This is our favorite Arasia flow, but now with this mass component. So here it's what Vitali was doing when he was a PhD student, and I saw him in Jena and thought, this is exactly what we need to do for this Wasserstein business. And so here it's just our famous, well-known Arasia flow, but here it's just a situation that when particles come together, they carry the mass, and then we have this inverse diffuse scaling of mass in the diffusivity. If you listen to what I just said, with this transformation of this noise by 1 over square root of mu, this is exactly what we need for this Dean-Kawasaki type noise structure. It's exactly what we need for this Dean-Kawasaki noise structure. Scaling by mass. It's exactly the thing. And okay, Vitali managed in a very nice paper. There's a little bit of a problem if you start from mass particles which have 0 mass, then they blow up at 0 time. But with some compactness arguments and so, Vitali managed to cook up a precise model for this, which is, we have no uniqueness, and Vitali doesn't have a uniqueness in law, but it's basically our favorite Arasia flow description, but now with this mass scaling in the interaction. So it's pretty much what we all know, and Vitali managed to cook up this thing even for time equals 0 to have this thing. And then if you have this modified Arasia flow, you can push forward Lebesgue measure. And with Vitali, a little later, we identified that this satisfies again the Dean-Kawasaki type equation. This is this noise scaling, but now the Laplacian in front is not really a Laplacian, but it's more or less like this Laplacian on the support of the measure. So we have finite, like in the Arasia flow, we have finitely many particles at every moment. And so the distribution here is really that you basically evaluate the second order derivative of the function of the support, but that's all information that you take from the mass. So that's a nonlinear version of Laplace operator. So you see, this is a Laplace. This is something like a Dean-Kawasaki equation, but with a very special scaling regime, and where the governing generator is not quite the Laplacian, but the brother of the Laplacian. And one should also note the fact that if we work with particles which all have the same mass, you don't see a difference between this Laplacian, this version of Laplacian. Okay, and that is in the same paper. We can manage to show that the short-term asymptotics of this process, again, exhibit the Wasserstein distance. So it's really, again, so if you ask yourself, how far are we away? You start this with the Lebesgue measure on unit interval, and you ask yourself, what is the next measure that you see after this evolution? Then it is basically asymptotically distributed according to the Wasserstein distance, which is natural.
What does it mean, nice
non-empty interior, essentially, something like that. It's just it is a measure to which you can apply, if you like, the corresponding large deviations result for both from inside and from outside.
Yes. So this time, actually, already this So I said to Vitaly that this is like large deviation.
This is a conventional large deviations result. This is honest large deviation. This is an honest large deviation. And the proof here, I mean, basically Vitaly did all the work here. This is really using Gesana formula, doing estimates. And so that's the honest full large deviations discussion using basically Gesana style formula. Okay, last example, and then I stop. Last example is modified Arrhenia flow, but reversible with splitting. So we like this model a lot when we did it, because in a way, this, in my view, this model here is the sticky behavior. If you compare this guy, the stickiness, the trajectories here resemble pretty much the trajectories that you saw in this model. Trajectories fluctuate along as long as they are alone. When they come together, they form a more or less bigger particle, which as a bigger particle diffuses less, and then they break up again. So in a way, this model here, but this model here still had this Laplacian in front, and the model that we did with Vitaly, this modified Arrhenia flow, is more or less like this model, but without the Laplacian operator. So therefore, it is no surprise that we get atomic measures only, because the Laplacian, the smoothing of the Laplacian is not there. And we were happy because this is, if you like, exactly the same picture, but without the Laplace operator in front. But this is not a reversible model. I mean, if you want to do some serious, I mean, if you want to sell this thing to a guy from statistical physics, he would want to see a reversible version of this. So we thought about how can we do a reversible version of the same model. And here is a simulation of a reversible version of the same. So this is, if you like, our modified Arrhenia flow, but now it starts from a single point, and now we have a mechanism built in which breaks up the particle at each moment and breaks up a smaller particle at each moment. And again, you have this characteristic scaling of mass versus diffusivity. Sorry. So if you zoom into this part here, you see you have a particle which is relatively heavy, it's not so quickly, and then it breaks up, and then these individual guys diffuse much wider. This is again the splitting, and this is really a generalization of the Arrhenia flow, but now with the splitting mechanism. And the description here, I would like to highlight this wonderful paper of Vitaly about the modified Arrhenia flow. He gave a description by compactness, doing finite systems, and being able to pass to the limit in the description of the characteristics of this field. But in the construction of this reversible guy, since we are looking for a reversible guy, we again use Dirichlet form techniques, which is really different from this field construction, from this field description. So the Dirichlet form theory always starts with constructing an interesting invariant measure. I spare you the details, but Vitaly has again constructed a wonderful new invariant measure. And then we have some gradient operator in this dynamics. So now we basically do full scale infinite dimensional analysis. This is, if you like, a version of Malliavin derivative of certain functionals on measure space, on a certain L2 space, on an infinite dimensional L2 space with respect to some version of a Gaussian measure. But this measure here, so for everyone who is familiar with white noise analysis, this is more or less like a white noise gradient type energy expression, where this would be Wiener measure. But here we do not do Wiener measure, we do a new invariant measure, which is totally non-Gaussian. And here we use a gradient, which is something like a Malliavin gradient, but not in the conventional Malliavin gradient case. But nevertheless, if you are familiar with some of the technology, and if you can do an integration by parts formula, so here we have something like an infinite dimensional integration by parts formula, which is really absolutely fantastic. Again, it was more or less cooked up by Vitaly. So you have really super cool infinite dimensional Malliavin style calculus on this measure value world. And that allows you again to construct the process by Dirichlet form methods, which is this process. You have an abstract Markov process, a Markov generator on an infinite dimensional space. And we can again identify the intrinsic metric. We can show that this Markov process, we can first of all identify. So let me just read out the statement to you. This is the theorem that we did. Eta is the parameter of the model. Then we have an invariant measure, which is parameterized by the eta. Then we can cook up an invariant measure, which is fully supported in all probability measures with finite second moment. And we have this energy form. This is a closable Dirichlet form. It's a quasi-local Dirichlet form on this space. And then there is, by abstract theory, and a properly associated diffusion process with a certain lifetime. It solves a certain martingale problem. So you can test this process against smooth test functions. You can find that this solves the same martingale problem as we have seen before. It has the right quadratic variation process. So this is more or less saying that this guy solves again the Dean-Kawasaki type equation. It's a martingale solution to this Dean-Kawasaki equation. And there's more things to say about this process, but in particular, this reversible coalescing, fragmentating, modified Arasia flow again satisfies a short-time asymptotics formula, which is given by the quadratic Wasserstein distance. So you see, now we're back into these flows and stuff. So we have an object which we think is quite nice. It poses a lot of questions. And it looks pretty much like a reversible Arasia flow, but it's not quite the same thing. And it is really substantially connected to this Dean-Kawasaki equation, versions of it. And it is also connected to optimal transportation. So that's the end of my talk. I thank you for your attention, and I thank Vitaly for all his cooperation over the last couple of years. Thank you very much.
Okay, thank you very much. Maybe some questions or comments, please. Actually, I have a following question. Can you just show again the equation with divergence where you have only singular solutions?
Yes.
Singular.
Yes. Wait 1 second, please.
Okay.
1 second. I show it to you. 1 second, please.
So we just
Here is this one.
Yes. We just want to keep the dynamic structure on the Riemann.
Yes.
line.
That's true.
Because if we want to have some, we can add this mechanism from Dawson.
Yes. Yes. Yes, we could.
Then we can then probably we can get the diffusion version.
Yes, but so first of all, here, yes, you could do that, but a little bit of a problem. We want to stay in conservation 1, so we will have changes of that is a problem. In another way, if you add other types of diffusion than this type of diffusion, in some sense, you produce a process which is not 100% intrinsic in the geometry that you want to do. Yes. We want to have, yes.
So the main claim is that if you keep this classification the basics and stuff, then you get only such solution.
Yes.
But from the main point of view, it's like thank you.
So I would also mention this, that you can do you can do the Dawson-Watanabe process. And then you can basically, this is a process which assumes values in measures, and then you basically can condition, there's a reasonable concept to condition the Dawson-Watanabe process to stay in probability 1. And then what you get there is this, which is sometimes called the Fischer-Bhattacharya distance, which is another Riemannian distance on the space of probability measures. So it's a classical paper by Peter March or something like this, which is more or less related to what's the name of like this Fleming-Vio process. So basically, yes. And yes, exactly. Right. So if you condition this thing more or less, if you condition this thing to be probability measure valued, the conditioning procedure, you basically arrive at Fleming-Vio. And the intrinsic distance of Fleming-Vio is Fischer-Bhattacharya metric, which is really very different metric. It's for other purposes, but it's not physical. This Fischer-Bhattacharya is more a statistical distance and not a physical distance. And here the challenge is really to have this physical distance.
Thank you very much. It was very interesting, and it is interesting always to have the relationship with physics.
Yes, I think so too.
Okay, thank you very much.